Looking at section 3.5, part 2, logistic growth model. It says the mathematical model for limited logistic growth is given by f of t is equal to c divided by 1 plus a e to the negative bt, or instead of function notation f of t, the function in regards to the time, they might just call it a is equal to the same setup. It says a, b, and c are constants with c is greater than 0 and b is greater than 0. So it says underneath, as time increases, meaning as t approaches infinity, the expression a e to the negative bt in the model approaches 0. It says, and as a gets closer and closer to c. It says this means that y is equal to c is a horizontal asymptote for the graph of the function. Thus, the value of a can never exceed c, and c represents the limiting size that a can attain. So in general, what's going to happen is we're going to look at some sort of growth that is going to occur and reach a very top limit. It's never going to actually equal that top value, right? That's what our asymptote is. It gets really close to that number, but never reaches that number. So pretty much what they're saying is this a times e to the negative bt, whichever function you want to look at, they're saying as that t is approaching infinity, the bigger time gets, the more time goes by, this whole thing, it says, is going to approach 0, which means that there's really not a piece here. Meaning you have c that's going to divide by 1, which is just going to equal c. So let's take a look. A little graphic that they had included on page 470 if you wanted to go and read some more information about it. What they're saying is you're going to start at an original amount. When t is equal to 0, you're starting at an amount, and it's going to grow for a while. And then eventually the growth is going to start getting lesser. It's going to still grow, but it's going to be at a decreased rate. And it's going to get as close to this horizontal asymptote as possible. That horizontal asymptote was that c value that they had on the top of the fraction here. Okay, so let's take a look at an example. It says, in a learning theory project, psychologists discovered that f of t equals 0.8 divided by 1 plus e to the negative 0.2t is a model for describing the proportion of correct responses, f of t, after t learning trials. It says, find the proportion of correct responses prior to learning trials taking place. Well, if we're talking about those prior to learning trials taking place, prior to doing anything, that means t is equal to 0. No time has gone by. What is our starting point, right? T is going to equal 0. So if we take and use our function and replace our t value as 0, let's see what we get. We're going to have a 0.8 divided by 1 plus e to the negative 0.2 times 0. Well, if I have a negative 0.2 times 0, that's going to give us 0. That means I have an e to the 0 power, and anything to the 0 power is equal to 1. So that means we really have a 0.8 divided by 1 plus 1, because this was equal to 1, which means we have a 0.8 divided by 1 plus 1 is 2, and if we divide that, we end up with a 0.4. That means that our f of t, the value of the function at 0, before any learning has gone on, we have a 0.4. So prior to learning trials taking place, the proportion of correct responses was 0.4. Now, if I take and look at what happens in the situation after 10 learning trials have occurred. So now we're going to look at what is the value of our function at 10. That means I'm going to plug in t is equal to 10. So that means that we end up with a 0.8 divided by, what do we have? 1 plus e to the negative 0.2 times 10. And if we simplify that down, let's see. A negative 0.2 times 10, well, that's going to end up giving us a negative 2. That means we have a 0.8 divided by 1 plus e to the negative 2. And we can kind of figure out, let's see if my handy dandy calculator is going to work so well on that one. Let's see, if I take a 0.8 and I divide it by, oh, I don't want that little extra thing. It's going to give me hassle. All right, if I take a 0.8 and I divide it by, I'm going to have a 1 plus e to the negative 2. we end up with a 0.70, so approximately a 0.7. So when we had 0 trials, right, we were at 0.4, and now after 10 trials, we're at a 0.7. So after 10 learning trials, the proportion of correct responses was 0.7. So it says, what is the limiting size of f of t? The proportion of the correct responses as continued learning trials take place. So no matter how many more learning trials that take place, remember, the longer, as far as t is approaching infinity, that means that e is going to end up going to 0, which means we have that 0.8 divided by 1. So the greatest value that we're going to end up with is a 0.8. So if we got to 0.7 after 10 trials, I think that's pretty good. So that limiting size, same thing, that was a 0.8. I think I put that in the wrong spot, sorry. All right, the next part talks about Newton's law of cooling. Now, Newton came up with this theory that if you take something hot and you put it in a room that's colder than the temperature of, say, your hot coffee or hot chocolate, that it's going to cool to the temperature of the room over time. So it says that the temperature T of a heated object at time T is given by capital T, it's going to be confusing, sorry. Capital T is equal to C plus, in parentheses, the T sub O minus C times e to the KT, where C is the constant temperature of the surrounding medium, meaning the temperature of the room, or if you're outside, the temperature of the outside air. T sub O is the initial temperature of the heated object. So I took that coffee and I made the coffee, the temperature of the coffee from the starting point. Usually a sub-zero is an initial amount. It says K is a negative constant that is associated with the cooling object. So let's see what we got. An example, an object is heated to 100 degrees Celsius. It is left to cool in a room that has a temperature of 30 degrees Celsius. Now, I know you know some things about Celsius and Fahrenheit. So 100 degrees Celsius, that's talking about boiling, right? 100 degrees Celsius is the boiling point, whereas 0 is the freezing point. So this says it's in a room that is 30 degrees. And if you want to look some things up, a comparison, 30 degrees would be an 86 degree Fahrenheit room. That's really, really warm. Usually rooms like 72-ish. So this says after 5 minutes, the temperature of the object is 80 degrees Celsius. So we went from 100 degrees to 80 degrees. It says use Newton's law of cooling to find a model for the temperature of the object T after lowercase t minutes. So we are going to look for our initial temperature. What are we starting at? The object is heated to 100 degrees Celsius. That's our initial temperature, which means that's our T sub O, the starting point. So that means we are going to have an initial temperature of 100. And then we have the constant temperature of the room is 30 degrees. So that means we're going to have 30 in 2 places. And then we have after 5 minutes, so 5 minutes, 5, we're going to have a 5, but we still need that the K value. They give us a time T, but they don't give us K. So we're going to have a variable K hanging out up here. And then the temperature after 5 minutes, they tell us it is 80 degrees. So just kind of filling in the pieces. So let's simplify this down. If we have, kind of shrink it down, we're looking at 80 is equal to 30 plus we have, you could probably do that in your head, the 100 minus 30, but for the sake of writing it all out, we have e to the 5k. We are going to take that and we are going to simplify it down to figure out what is that k value. So solve to get k all by itself. Let's start by subtracting 30. If we subtract the 30, we're left with 50 is equal to, let's simplify those parentheses, 100 minus 30, that's going to give us a 70 e to the 5k. And then we're trying to get the k all by itself. So that means we're going to divide by 70 and divide by 70. 50 over 70, I'm just going to call that 5/7 because that would be simplified. We have an e to the 5k. Well, in order to solve for an exponent, we need to take the natural log of each side. So ln, natural log of each side. That allows us to have an ln of 5/7 is going to equal, well, if I have the ln of e, remember that cancels that piece out, it's just going to leave us with that 5k. So 5K. And then we could divide by 5 to get the K all by itself. So find a handy dandy calculator. We have the ln, or the natural log, of 5/7 that we have to take and divide by 5. We end up with a negative 0.06729. So how about we call it 673? 673. That means we can rewrite our final equation. The equation of the model is, now we go back to that initial, it's going to be t is equal to, we had the 30, that's our starting point, plus we had 70 because we had simplified that 100 minus 30 down. And I'm going to run out of space because I'm writing a little too big. I'll write it up over here. So then we're going to have 70e to the negative 0.0673, and then t, just in regards to total number in general time. Let's shrink that down a little bit. We'll keep that open. All right, so we took and we found an equation. Let's use the equation. So the object is heated to 100 degrees Celsius. It's left to cool in the room that has that temperature of 30 degrees Celsius. After 5 minutes, the temperature of the object is 80 degrees Celsius. What is the temperature of the object after 20 minutes? So now all we're doing is using this equation that we just wrote, but now they tell us we have 20 minutes. That means in terms of our time, we now know that t is going to end up equaling 20. And so I don't remember if it's done on your paper or not, but in place of t, we're going to plug in 20 and throw that whole ugliness into the calculator. We end up with approximately 48 degrees Celsius. I think I had some typos on mine compared to yours. So if you don't have that filled in, and pause it and fill that in. And the next part of that, again, still the same object, 100 degrees Celsius, left to cool in the room that is 30 degrees Celsius. This one now tells us that after 5 minutes, the temperature of the object is 80 degrees Celsius. When will the temperature of the object be 35 degrees Celsius? I'm going to get rid of that because I like a slightly bigger writing area. All right, so if we go back to our original model, our equation that we had was t was equal to 30 plus 70e to that ugly 0.0673t. And now they want to know in terms of when will the temperature of the object be 35 degrees Celsius. So I want to know when our temperature T, I'm going to take this over here, is going to be 35. That means 35 is equal to 30 plus 70e to the ugliness. And now we have to figure out how much time is going to go by to hit that 35 degrees Celsius. So solve that out. Subtract your 30. We'd have 5 is equal to 70e to the negative 0.0673t. Get rid of the 70 by dividing. You can keep it as a 5 over 70, or if you want to simplify it down, it makes a 1 over 14. Is equal to our e to the negative 0.0673t. Natural log of each side. To end up then canceling this out. So that means we're going to end up with t is going to equal, we're going to have that ln of 1 over 14 divided by the negative 0.0673t. I kind of skipped a step or two if you guys are okay following along at this point. So plug it into your handy dandy calculator. I'm going to avoid that for right now. You should have ended up with approximately 39 minutes. So if your calculator doesn't give you that, double check some parentheses and how you have your divisions set up. And the one last piece that we're going to look at, it talks about modeling data. So choosing an appropriate model for data. It says throughout the chapter, we have been working with models that were given. However, we can create functions that model data by observing patterns in scatter plots. So it says figure 3.24 shows scatter plots for data that are exponential, logarithmic, and linear. So depending on the type of information you have, the first type is what happens when we have exponential, right? Notice that we have that horizontal asymptote at 0. The next part talks about our logarithmic functions. That's where we have that vertical asymptote at 0. And then the other piece talks about linear, right? Something that is looking like as you look at the data, it's going to end up making a straight line. So the last piece. It says the table shows the populations of various cities in thousands and the average walking speed in feet per second of a person living in the city. Look at this data. What do you think is happening? Exponential, logarithmic, or linear? That's going to be logarithmic. So the last piece is expressing y equals a b to the x in base e. So if we have y is equal to a b to the x, that can be rewritten as y is equal to a times e raised to the natural log of b times x. So all that's doing is taking and introducing this base of e raised to the power ln. And if you remember from some of our previous properties, e raised to the ln kind of cancels each other out to just leave us with that bx. So let's use that in one last example. It tells us to rewrite y equals 4 times 7.8 to the x in terms of base e, express the answer in terms of a natural logarithm, and then round to 3 decimal places. So if we have y is equal to 4 times the 7.8 to the x, that means that we can still have our 4 in the front there. So y is going to equal 4 times, but we're going to take this as a power or a base of e and raise it to the power of the natural log of 7.8. That's going to multiply with that x. And now that I have that, I can simplify down. I can take and throw in my calculator an ln of 7.8. So that's going to give us y is equal to 4 times e raised to the 2.054x.